Welcome to the deep dive. Today, we're tackling something pretty fascinating, how to turn agricultural waste,
Mhm.
stuff like rice husks, things people usually just throw away,
Yeah.
into actual usable gas for energy.
Yeah, it's a great topic.
We're basing this on a really, really detailed engineering guide about building biomass gasification models. It gets quite technical, but don't worry, we'll unpack it.
We will?
And just so everyone knows, this is episode 6 of our Third Way Energy series. We're actually on a 156-week journey looking into these tri-hybrid systems, solar, biomass, hydrogen, all working together.
That's right. And what's fascinating here, I think, is that our source material, this deep dive from cakeles.com, it really cuts through the complexity. Our mission today isn't like to drown you in equations or code.
Definitely not.
No, it's more about getting the core ideas, the why it matters, and, the really crucial insights if you're curious about these kinds of sustainable energy solutions. We want to strip away the jargon.
Okay, let's unpack this then. The source jumps right in with a really obvious question. If you've got a pile of rice husks, why not just, burn it?
Right.
Set it on fire. Seems way simpler than this whole gasification thing.
Right.
Add air, get fire, heat, steam, turn a turbine, boom, electricity. Easy.
It sounds easy, and that's a perfectly logical first thought. The source actually tackles this directly in a section called Why Not Just Burn It? And if we connect this to the bigger picture, it's not just about the tech, is it? It's an economic choice, an operational one, too. Think of direct combustion like, I don't know, a big bonfire. Simple, yeah, but maybe not very efficient. You get heat, sure, maybe boil some water, but efficiency, probably hovering around, say, 20–25%.
Okay.
And it mostly just makes heat or steam. If you want electricity directly, it's less versatile. Plus, you tend to get more emissions, more smoke.
Less control.
Exactly. Now, gasification, that's more like your high-tech oven. It's definitely more complex to set up and run, no doubt about that. But you get higher efficiency, maybe 30–35%. And the key thing is it produces this really versatile fuel gas. They call it producer gas, or syngas.
I think he's right.
And that gas can directly run engines or turbines. Plus, if it's working right, the emissions are generally cleaner.
Okay. So there are trade-offs.
Big trade-offs. You choose gasification specifically when you really need that electricity output, when you have skilled people to run the thing. Keep those temperatures consistently above 800 Celsius.
That sounds hot.
Oh, it is. And you need to keep the moisture in your biomass, like those rice husks, below about 15%. So yeah, complexity versus control, versatility, and better efficiency.
That makes a lot of sense. Campfire versus the fancy kitchen oven. Got it. But is that extra efficiency always worth the hassle, the cost?
Yeah.
Especially maybe for smaller setups.
Well, that's the question, isn't it? Scale matters. For maybe a small community just needing basic heat, maybe direct burning is fine, good enough. But if you're talking reliable, cleaner electricity for a grid, or maybe a consistent fuel source for an industrial process, then that investment in gasification often starts to make a lot more sense.
Okay. So speaking of what actually happens inside this fancy oven,
Yeah.
what's the process? You put the rice husks in. Does it just sort of poof into gas? Or is it more complicated?
Definitely no poof. It's much more elegant than that. Think of it like a 4-act play, chemically speaking, happening at different temperatures as the biomass moves through the gasifier.
A 4-act play, okay.
Act 1, from about 25 up to 150 degrees C, is drying. Simple enough, the water just boils off.
Right, get rid of the water.
Act 2, things heat up to maybe 150, 500 C, that's pyrolysis. This is where the biomass itself starts to break down, decompose, but without fully burning. It turns into char, some volatile gases, and crucially, tars. We'll come back to those.
Tars. Sounds ominous.
Yeah.
Okay.
Act 3, hotter still, 500 to 900 C. This is oxidation. Now, this isn't full combustion, it's partial. You let in just enough air to burn some of that char. And this step is absolutely critical because it generates the heat needed to drive all the other reactions. It's the engine room, basically.
So it burns some fuel just to power the process itself.
Precisely. And then Act 4, the grand finale, is reduction. This happens way up at 800 to 1,000 degrees C. This is where the main event happens, forming the useful gases like carbon monoxide, CO, and hydrogen, Euro. You have reactions like the Boudouard reaction turning CoO into C, and the water gas reaction making hydrogen. These are the valuable products.
Okay, CO and H2O, combustible gases.
Exactly. But here's the catch. Some of these key reactions absorb heat. They need energy input. Others, like that partial oxidation, release heat. So you've got this incredibly delicate energy balance. The heat-releasing parts have to generate just enough energy to fuel the heat-absorbing parts. Get it wrong, too little heat or too much heat escapes, and the whole thing just stops, grinds to a halt.
Wow, okay. So even before you get the good gas, you've got pyrolysis making tars, then this controlled burn just to fuel the main reactions.
That's
Yeah, that sounds like a delicate dance, all right. How on earth do engineers keep that balance? What are the actual controls?
That really is the key challenge keeping that dance going. The source zeroes in on three absolutely critical parameters, like the non-negotiables. First, and maybe the most vital, is the equivalence ratio, or ER. Basically, it's how much air you're actually feeding in compared to the perfect amount you'd need to burn everything completely.
Okay.
You need a real sweet spot for good gas quality, an ER between 0.25 and 0.35.
Not much wiggle room there.
Not much at all. Too little air, say below zero point 0.2, and it's not hot enough, the reactions fizzle out. Too much air, above 0.4, and you're just burning too much, making poor quality gas. And if you hit an ER of 1.0, well, you're just doing direct combustion again.
Which defeats the purpose.
Right.
What's next?
Next are the temperature zones. We just talked about those four acts: drying, pyrolysis, oxidation, reduction. Each needs its specific temperature window, from around 100 C for drying up to 900 C or more for oxidation and reduction. Maintaining those distinct zones is crucial.
Makes sense.
And the third,
Residence time. This is simply how long the actual biomass spends in each of those temperature zones.
the timing.
Exactly. And it's a real Goldilocks problem. Too fast, the reactions don't complete, you don't get full conversion to gas. Too slow, you can end up making way too much of that nasty tar.
Ooh, tar again.
Yep. The source gives some typical times, maybe 5–10 minutes for drying, 10–30 for pyrolysis, but then oxidation is super quick, like 1–2 seconds, and reduction is maybe 2–5 seconds.
Wow, seconds for some stages.
It really highlights the precision needed, which does raise the question, how do engineers nail all this, especially when your input fuel, the biomass, can be so variable? Yeah, that's what I was thinking, because it sounds like there are many ways for this to go wrong. For every success story, you hear about projects that just didn't work out. Let's talk about the dark side of gasification. What are the common pitfalls?
Absolutely. The things that turn promising tech into, well, an expensive headache. Our source points out three main culprits, the big failure modes. Number one is that tar formation we keep mentioning. This is usually because the temperature, especially down in that reduction zone, isn't high enough. It dips below that critical 800 degrees C mark.
Okay.
When it's too cool, those heavy hydrocarbon molecules made during pyrolysis, they just don't crack apart into lighter gases like they're supposed to. They stay as this thick, sticky, gooey tar.
Like trying to run an engine on treacle.
Exactly, and it gets everywhere. Clogs, pipes, filters, engines. It can basically gum up the whole works and make the system unusable. The source actually has this example calculation. If you're running at only 700 degrees C with 20% moisture and an ER of 0.3, you could be producing something like 45 grams of tar for every cubic meter of gas.
That's a lot of gunk. Yikes. Okay, so tar is bad. What else goes wrong?
The second big one is ash sintering. This is the opposite problem. The temperature gets too high.
Too high. How high?
Higher than the melting point of the ash in your specific biomass. Different stuff melts at different points. Rice husk ash is pretty resilient, melts around 1400, 1550 C. But something like bagasse ash melts much lower, maybe 1050, 1200 C.
Oh.
When that ash melts, it forms this kind of molten, glassy slag. Then it cools and solidifies, blocking the airflow through the reactor. It can create a solid barrier, basically choking the process, and it's incredibly hard to remove.
Okay, so avoid tar by staying hot. Avoid sintering by not getting too hot, depending on the fuel. Tricky. What's the third one?
The third is maybe less dramatic, but just as effective at stopping things: bridging. This happens when the biomass particles themselves stick together inside the reactor.
Oh.
Often because they weren't sized properly to begin with, or maybe there's too much moisture making them sticky, they form a sort of arch or bridge over the space below.
Like a dam.
Kind of, yeah. And it just stops the flow of fresh biomass down into the reaction zones. The fire goes out below, the process stops. Prevention here is more straightforward: proper sizing, proper drying.
Man, it really does sound like a minefield. Tar, melted ash, blockages. What are the absolute must-dos then? The golden rules to avoid disaster.
Yeah, the source really hammers this home. Rule 1, keep that temperature above 800 C, especially in the reduction zone, to kill the tars. Rule 2, keep moisture below 15%. Rule 3, nail that equivalence ratio. Keep it in the 0.25 to 0.35 range.
Okay.
Rule 4, have a plan for tar. Don't just assume it won't be a problem design for tar removal or minimization. And Rule 5, size your biomass correctly to prevent bridging. A lot of failures, the source suggests, come from just, well, Trusting the glossy brochure, maybe undersizing the equipment, forgetting about moisture, ignoring tar, assuming everything will just work perfectly.
Right. Assuming success instead of planning for failure.
Exactly. Good engineering, as the source puts it, is about predicting failure modes, not just hoping for the best.
That's a really powerful point. Thinking ahead about what could go wrong seems way smarter than just being optimistic.
Right.
But okay, despite all these potential nightmares, when it does work, it's pretty impressive, right? The source had an example.
It does, yeah. A design example for a gasifier meant to handle 100 kilograms of rice husks every hour. We don't need to get into the weeds with the calculations or the Python code mentioned.
Please don't.
No. But the results are really interesting. They show how you can predict the outcome. For instance, that 100 kilogram system, it takes in about 1,400 megajoules of energy per hour from the husks. And the model predicts it should output around 980 megajoules per hour as useful syngas.
And that translates to actual power.
Yeah, potentially over 272 kilowatts of power output. The models also help figure out practical things like how much air you need and even the physical size of the reactor in this case, something like just under a meter in diameter and about 5 meters tall. It makes it tangible.
It really does. It shows the value of doing that homework up front.
Absolutely. And that's what the source emphasizes in its real-world validation bit. It calls these models honest. They might not be perfect, but they predict the problems, the kinds of issues that, as it says, usually hide in the brochure and proposals.
But they do.
So using these models, even knowing they have limits, is just crucial for robust design. It helps you avoid those really expensive failures down the line. The author even shared an interactive tool, a Google Colab notebook, basically a training tool, so people can actually play with the numbers themselves, change the ER, change the moisture, see what happens.
Oh, cool.
Which, raises an interesting question for you listening. Where in your own work, or even just life, could applying this kind of rigorous prediction, this precision, make a difference compared to just, guessing or hoping for the best?
That's a great question. Wow, what a journey we've been on. From just a pile of old rice husks to this complex, sometimes challenging, but ultimately really promising technology. It really shows how smart engineering can take waste and turn it into a real energy resource, provided you understand that delicate dance of chemistry and temperature.
It really does. And it comes back to that idea, good engineering is fundamentally about predicting how things might fail, not just assuming they'll succeed. It's about testing, understanding limits, designing for the challenges. So maybe a final thought to leave you with, something the source inspires. What area of your work or your life could benefit from actively anticipating the challenges instead of just crossing your fingers and hoping everything works out?
A powerful thought indeed. Well, thank you for joining us on this deep dive into biomass gasification. That was episode 6 of our Third Way Energy series. We really hope you leave with a clearer picture of how this works, the hurdles and the potential, and maybe a bit more appreciation for the detailed work engineers do. Until next time, keep digging, keep questioning, and keep learning.